There are two types of exponential functions we're going to be looking at and that you need to identify. One is growth and the other is decay. Growth, you can tell by looking at the equation, your b value is going to be bigger than 1. So in other words, when I'm raising to my exponent is going to be bigger than 1. That's growth. If we look down here at our graph, we say it's growth because it's growing. The other one is decay, and that is your b value is going to be a fraction. It's going to be less than 1. Obviously, it's got to be bigger than 0. And we can see because it's shrinking. Now, both of these exponential function, notice they never go below 0. That 0 is called your asymptote. And today, everything's going to be 0. That'll change later on, but today everything's going to be 0. So in other words, it gets closer and closer to 0, but it never reaches 0 because remember, an exponent doesn't change the value. It makes it a reciprocal. If the exponent's negative, you'll get a reciprocal. The exponent doesn't make the number negative. For both of these, your domain is going to be all real numbers. Also, your range is going to be positive numbers, that's as we talked about. You're always going to have one intercept and no x-intercepts. Your end behavior. Notice growth, it's getting bigger. Decay, it's getting smaller as you go to the right. And then if you go to the left, it's just backwards. That is, on growth, as x decreases, so does y. But it just never reaches 0. And as x decreases, y increases with decay because you're going backwards. Those are the key functions I want you to identify when we do a graph. So let's take a look at example 2. It says each time you fold a piece of paper in half, it doubles in thickness. If the piece of paper was 0.05 millimeters thick, then you can determine the thickness of the paper given the number of folds with this function. Y equals 0.052 to the x power. I want to identify the key features of this function. I want to graph it. And I want to identify the relevant domain and range in the context of the situation. First off, when we're talking about is it growth or is it decay, look at your b value. My b value is bigger than 1. So I know this is exponential growth. And if you ever watched Mythbusters, they did something that there used to be a rumor that you could only fold a piece of paper a certain number of times. It gets too thick to fold, and they did it, and I think the magic number was 8, and they showed it was 9. Of course, they used this huge piece of paper, and they used forklift, so not really realistic for what we do in normal life. My domain, remember, that doesn't matter if it's growth or decay, it's all real numbers. My range is going to be greater than 0. We know that no matter what. My y-intercept is going to be when x is 0. So what's 0.05 times 2 to the 0 power? Well, we know anything to the 0 power is 1. So I'm going to get 0.05 from my y-intercept. Just like anything, we are going to make a table if we don't understand how to graph it. So we're going to start here. So I'm going to do x and y. Now, within context of the situation, can x be negative? Can you have a negative number of folds? No. So I'm going to start at 0, and I'll do a few of these. I'll go 0, 1, 2, maybe I'll go to 3 so we get the idea. So now, I already know when x is 0, I get 0.05. When x is 1, that'll be 0.05 times 2 to the first power. Well, 0.05 times 2 to the first power, that's 0.1, isn't it? And then I could go 0.05 times 2 squared. 0.05 times 2 squared is 0.2. And then 0.05 times 2 cubed, that's 0.2 cubed is 8. So 8 times 0.05 is 0.4. So we could graph this by hand. I would start here, let's go like 0, 1, 2, 3, and then I'm shrinking. Well, actually, I'm not shrinking, I'm growing. So let's count by 0.1s. So 0.1, 0.2, 0.3, and 0.4. So when you're at 0, you're at 0.05. When I'm at 1, I'm at 0.1. When I'm at 2, I'm at 0.2. When I'm at 3, I'm at 0.4. You see how it's starting? At first it looks like it's linear, then it starts growing and growing and growing. Now, can I use decimals to do all this? Sure I can. But I'm going to have to still identify my key functions, but you can use decimals to verify it. So let's show you how you would do this. First off, whoops, I want my graphing calculator here. So let's get rid of that stuff. And, whoops. You can make a table, hit your plus sign, and then table. And notice the only thing is when I do my table, I have to use my subscripts when I do it. So I'll go 0, 1, 2, 3, 4, and so on. And then instead of writing y1, I think I'm going to type in my equation. Whoops. So I'm going to say 0.05 times 2 to the x power. It'll be x1 power. And there we go. Got it. Notice if I add more numbers on here, it's easier to see. In fact, if I go down here, if I type in my equation, y equals 0.05 times 2 to the x power. This one I don't have to use my subscripts. There I can see my graph. See how it's asymptotic towards 0? It never gets to 0. Now, it doesn't make sense to have negatives in this context because you can't have a negative number of folds. But if I look at the equation, if I shrink in, notice it gets closer and closer to 0, but it never goes through 0. And that's how we would do that one. So yes, you can use decimals, but you still have to do the key features. You might have to make a table by hand, but you can use decimals to help you make the table too. That just saves you some calculations. We're not really doing anything. Decimals isn't saving us any time. Well, it's saving us some time, but it's not saving us any knowledge base of what we have to do.